All right, good morning, everyone. Welcome to our first talk of this session. Our first talk is by Cory Zue on how do domain-specific chatbots work, an overview of retrieval augmented generation. All right, please take it away.
All right, thank you. And I will turn off. Okay, cool. Yeah, so I'm Cory Zue, and I am going to talk about domain-specific chatbots. So what are we talking about exactly? And so if you have been paying attention at all to like the startup scene in the last 6 months, watching places like Product Hunt, which is a website where people launch their startups, you might have seen something like this, like a custom ChatGPT for your data, or maybe something like this, ChatGPT over your company knowledge, ChatGPT for your website, turn your contents into a chatbot, or my own product, a private chatbot for your company data. And these are all different products, even though they look almost exactly the same, and they all are doing kind of the same thing, which is instead of having a general knowledge sort of like ChatGPT-like thing, you have a specific chatbot that knows about information that you've given it, and it can answer questions specific to your product that aren't necessarily in ChatGPT or any of the other language model bots. So one reason why these have exploded, and the reason that I kind of got into it, is due to a library called langchain. And so langchain, if you haven't heard of it, is a Python library that provides a lot of tooling around working with large language models, which is the technology that powers, GPT and all these other AIs. And the really impressive thing about langchain is that in just 3 lines of code, so you've got these 2 imports here, and then these 3 lines of code, you can basically create one of these custom chatbots. And so in this example, this will create a chatbot specific to Paul Graham's essay, How to Do Great Work. And then when you ask it a question, which you can see in the UI here on the left, it will, instead of just providing sort of like a generic answer that ChatGPT might provide, it will provide answers that are very specific to the essay that you've given it. So in this underlined example, you can see it says, work on something you have a natural aptitude for and deep interests in, which it has pulled from this part of the essay here on the right. So this is pretty cool, and it definitely has tons of use cases, both sort of across academia, companies, all sorts of places. And yeah, just for comparison, this is a what happens if you ask even a good language model that question. It'll just give you sort of a generic thing about personal development and health and fitness, blah blah blah. So yeah, these are really interesting. They're really useful, and I'm going to talk about how they work. And this will be pretty high level. It'll be pretty theoretical. That's not going to be too much coding or anything like that. But hopefully by the end of this talk, you'll have an understanding of what these things are doing and some of the common use cases and ways that you can build your own, optimize them, problems you might run into, etc. First off, what this isn't. So this is not chatting with a document. Like if you've ever uploaded a PDF to ChatGPT or to Claude, that is something different. That is taking the whole document and basically inserting it into the chat. That's not what this talk is about. It doesn't have anything to do with training models. It doesn't have anything to do with fine-tuning. Those are also useful things, and you can do interesting stuff with them, but that's not what this talk is about. Everything in this talk you can do basically with API calls to, standard language models without having to do any customizations of your own. Cool. So the way that these work is a process called Retrieval Augmented Generation, which is a bit of a mouthful, and so people often refer to it as RAG. And basically, it's the process of supplementing a user's input to a language model like ChatGPT with additional information that you've retrieved from somewhere else. And the language model can then use that information to augment the response that it generates. So that's also a lot of words. So it's probably easier to explain in a picture. And so here, starting on the left, you can see it starts with a question. So let's say you have some sort of documentation site, you built a knowledge base, and you want to provide a way for your users to ask questions about it. So they might say, how do I do something? And what that does is it goes into your knowledge base, and it'll basically do a search operation. This is the retrieval step, and it'll pull out what it thinks is the relevant knowledge to that particular question. Then it sends that knowledge to a language model like ChatGPT along with a question. And it's a lot like if you've ever asked ChatGPT to summarize a document or something like that. Basically, it's saying, okay, read this stuff, then answer this question based on that stuff. And ChatGPT or your language model of choice will happily do that and then give you your domain-specific answer. So I'm going to start at the end here, which is the augmented answer generation step, because in many ways, this is it's kind of the easiest one to wrap your head around if you've ever used ChatGPT or ever used a language model before. So I don't know how many of you have ever used the OpenAI playground. It's kind of a slightly more advanced version of ChatGPT. But basically, it's the same thing, except it also exposes, on the left here, it exposes the system prompt, which is it's kind of like your general instructions for ChatGPT. So for ChatGPT itself, the system prompt is basically like, you're a helpful assistant. Try to answer the user's questions, maybe something about your knowledge cutoff date or something like that. Then you have the messages, which if you've ever used a language model, you're probably quite familiar with. And then there are these model parameters that you can tweak, which I'm not going to talk too much about, but they exist. And so when you look at this, you can basically think of this augmented generation step as filling in these boxes on OpenAI Playground. So for the system prompt, we're just going to explain the task. So we're going to say, you're a knowledge bot. We're going to give you extracted parts of a knowledge base. We're going to label them with documents, and we're going to ask you a question. And then please answer that question using your knowledge base. Then we do that. So our first message is going to be this list of labeled documents. The AI will happily sort of read that and be able to understand it. And then finally, we ask it the question. And so if you went through the trouble of putting the system prompt in, taking the relevant snippets of the Paul Graham essay, putting those in under these document headings, and then asking, what should I work on? GPT would happily, provide basically the exact same answer. And that is exactly what's happening in this augmented generation step of the language model. So in code, you can see it's very straightforward. I've abstracted these things out to functions, but basically this is the OpenAI Python API. You give it your model you want to work with, and then you just give it a system prompt, which is that over here, you're a knowledge bot thing. You give it your sources, which is your formatted documents. You give it the question, and it will then respond with the answer. And that is basically all you have to do for this last step. So cool. So far, so good, hopefully. So now we're going to talk about retrieval. And retrieval is where a lot more of the complexity and interesting stuff lies. So what is going on here? What are we actually doing when we take somebody's question, we put it into a knowledge base, and then we pull out the relevant snippets that we're going to give to the AI? And the first thing that is worth understanding is that this is basically just a search operation. And so like Google, like any search operation, there's two big picture pieces. There's indexing, which is essentially taking that knowledge base and sticking it in something that can be searched and queried. And then there's querying, which is pulling out the relevant bits based on your search terms. And so you can use whatever search operation you want in here. So like if you've played with Bard or with Bing, like when those systems are giving you an AI answer, they're using their own like Bing search or Google search, and they're going and getting the websites. They're basically doing RAG and then answering based on the websites. When you're building these things yourselves, you're often doing it on a much smaller knowledge base, and you're not using sort of BART or Bing or Google or Bing. And instead, most of these things are built using something called semantic search, which is another core piece of AI technology. And it's built off something called embeddings. So I'm going to do a quick detour into what embeddings are, because I think they're one of the most interesting parts of the language model world. And they're also, understanding this is quite core to understanding a lot of how semantic search and how these different things work. So I'm going to start with kind of a high level question, which is, how do we know what words mean? And, somewhere in our human brain, we know that the word child is basically the same as the word kid. We know that red, green, and blue fall into a set of things that we call colors. We know that pleased, happy, and elated kind of represent the same feeling, but, a bit stronger as you go up through those words. And basically, like, somehow in our brain, we have our own language model. We have a way that we map words into meaning, and we have no idea, at least I don't think we have any idea what that looks like or how that works. But somehow humans do it. And AIs have to do this too. I mean, the way that AIs can respond to questions and do autocomplete and stuff is because they have their own intuitive understanding of what words mean. We don't really know what the AI language looks like either, but we can work with it. And so AI's representation of language can be translated into basically vectors of numbers. And so you can imagine we have a translator that goes from human language into AI language. And on the left, you would have a human, hello, how are you? And then you pass it through this translator to AI language, and it spits out a vector of numbers. So these vectors of numbers are called embeddings. That's what people are talking about when they use embeddings. So you could think of this thing as like an embedding machine. We don't know what these numbers mean. So like if you said, why is that number 3? Like, we can't tell you why that number is 3. All we know is that 3 is meaningful to the AI in its understanding of the human language. But what we do know is that the AI generates similar numbers for similar concepts. And so because they're numbers, we can also plot them. And so you can imagine taking these AI numbers, and obviously you can't plot them on a 2D axis if they've got actually, like usually over 1,000 parameters in those vectors. But you can imagine it like this. And so basically, if you have things that are very close together, like hello, how are you, and hey, how's it going, they're going to end up they're going to have very similar numbers. And if you plotted them, those points would be very similar or close to each other. Something like good morning, which is another greeting, would be in that same sort of neighborhood, but a little bit further away. And then when you have something totally unrelated, it ends up far away. And this is the core principle that guides semantic search. And this is why semantic search works if you use child instead of kid, even if none of the words actually match, because these numbers encode some meaning into those words and phrases. So coming back to how this fits into our retrieval step. So first, for now, we'll just assume that we have some way to take our knowledge base and turn it into little snippets. And we'll come back to that splitting snippet machine later. But once we have those snippets, we can then pass them through the embedding machine, the thing that translates the human language into the AI numbers. We get those AI numbers and we save it into something called a vector database. A vector database is basically just a database, but it is optimized for storing and doing lookups and query and math operations on these lists of numbers. And so once you have your knowledge base indexed in this vector space, you can plot it just like we plotted those words above. And so you can put each of these knowledge snippets in their 1,000-dimensional space. And then when you want to do a search query, you do this same closeness thing. So you take your user search query, how do I do X? You pass it through the embedding machine. I should say, the embedding machine isn't like this complicated piece of technology that you write. It's an API call or a function call if you're running the models locally. Then you get back these AI numbers. You plot those AI numbers, and then you basically do math to find what are the nearest knowledge snippets that match this term. And that's how you use semantic search to pull out the most relevant knowledge with these embeddings. In practice, what you're actually doing is called a closeness query. So you get the embedding, and you do a query in the vector database. There's a bunch of different ones that you can do, and people kind of discuss and debate. Should you use like a cosine search or a blah blah blah. That's one of the things that you can go down a deep hole fine tuning, but usually you can just kind of stick with the defaults and they'll work fine. And that will pull out the relevant knowledge for you. Just a quick sort of aside on vector databases. So this is one of the hottest spaces right now because tons of people are building applications on language models, and they're doing things with these embeddings. I think if you took this slide, probably the companies on this slide have raised like $500 million in the last year, maybe more. My personal recommendation, which is the same as my recommendation for Django applications, is just use Postgres. Postgres has a nice extension called pgvector, which you can add to your Postgres databases, and then you can do these embedding operations directly in your Postgres database. It's quite nice because, especially if you're building an app that has other data models, if you're using Django or something like that, then you can have everything in one place. You can define relationships directly to your embeddings and other things. That said, I haven't built anything that's huge scale. I haven't gone deep into optimizing these queries or anything like that. So I know like Pinecone is a very hot company right now. I'm sure they have a nice vector database, and obviously there's lots of options here. Right. So back to the overview. We have now covered retrieval. We've covered the augmented answer generations from the language model. And we've covered this line of code. So yeah, that one line of code is actually doing that entire sort of embedding vector database lookup, send it to the language model, get back the response. And you can see why LangChain caught on, because like the fact that you can just write 5 lines of code and be doing this directly in a Python interpreter is incredible, and it's super fun and magic to play with. What we haven't done is we haven't talked about these lines of code. So we made the assumption that we had this sort of knowledge split thing that created our embeddings in our graph, but we didn't really talk about how that works. So now we're going to talk about building the knowledge base. So yeah, so back to indexing, we covered this half. So we know what to do once we've got our knowledge split up and how to save that. But we didn't really say anything about how you go from a knowledge base to a bunch of snippets of text that you can use for your apps. And to emphasize, like, this is definitely the most important part of the whole thing, and it's also probably where like 95% of the work happens. So that LangChain demo works incredibly well, and it sets up all the defaults. And then if you want to make it better, you have to go down this long rabbit hole of optimizations that all have to do with mostly just splitting up this knowledge base and getting good knowledge snippets to do the search operations well. I break in my mental model, I break this step into two conceptual pieces. There's loading, which is basically getting the contents of the knowledge base out of where it is, and then splitting it up into chunks. This is kind of an arbitrary distinction, but it's also a similar distinction to the one made in LangChain. I find it's kind of helpful when you're building these apps to think of it this way. Loading is plumbing. And so like loading, you can imagine like scraping a website or scraping like, a bunch of websites from a sitemap file, extracting text from Word documents or PDF documents, like going and hitting an API and pulling down all of the text in an API. It is work for sure. There's also a lot of plumbing in terms of like, especially if you're doing interfacing with external services, there's like error handling and rate limiting and other stuff. But this is a very like tractable known problem that people have been solving for ages, like how to get text out of a website. So it's mostly solved. And one of the really nice things about LangChain is that LangChain ships with like 100 of these built-in loaders, and you can just sort of pass it, a link to Mastodon or Trello or Microsoft Word or WhatsApp, and it will. People have written essentially classes to go and get the stuff and send it back to you. So this is a really useful part of LangChain, and it's a really powerful way to index content from all sorts of different sources. Splitting is also plumbing, but it is much harder to get right. And so this would be like, okay, now I've got like the entire Wikipedia page on South Africa, but I want to split it up into little snippets that I'm going to embed. And like in a PDF document, you might want to break on pages. On HTML document, you might want to break on section headings. If you don't have any structure at all, then you kind of just cut off after a certain number of words. But this part is a part that you can spend a lot of time playing with, trying to get it right. And why do we need to split our documents? So if you recall how we're doing this retrieval step, each document gets plotted in this vector space. And so if you imagine a book, and let's say we were indexing like a chapter of a book, and in that chapter, a boy like goes to the store and he buys some groceries, and then he comes home and he plays with his dog, and then he has dinner, and maybe it's a boring book. But like if you then said like, okay, what's the name of the dog? Like the name of the dog might be in that chapter somewhere, but if you embed that whole chapter into AI language, it's going to get sort of like softened out by all the other stuff in there. So if we make our documents too big, then the embedding gets less and less meaningful. Basically, the more text you embed, the less sort of specific the embeddings get. They become quite flat, and then your searches don't work very well. At the same time, if you make them very, very small, then you don't have enough information to answer the question. So like if you imagine, like if you split on every sentence, and then you had a sentence that was like, here are the instructions for downloading a PDF file, and then you had 10 more sentences explaining the instructions, like it would match that sentence telling you about the instructions, but it wouldn't match the actual instructions themselves. And so when you pass that to the language model doesn't actually have the information it needs. It only has like the part where you ask the question. So this is definitely like a complicated and interesting optimization problem that you can spend a lot of time iterating on and trying to get right. It often, to produce really good bots, you often almost need someone to just go through by hand and do it sort of visually, which is why the platforms that create these automatically with sort of like no work, like they still don't work all that well. This is just to summarize, and actually I'll skip ahead. So this is now the whole pipeline with all the details filled in. And so we just talked about indexing. And so on the indexing side, we take our knowledge base, we're going to load it, we're going to split it up, we're going to take those little snippets and turn them into our AI vector embeddings. We're going to save those in a vector database. And then during retrieval, we'll take the incoming question. We'll do that same embedding translation. We'll do a closeness query to find the most relevant snippets. We then pass those snippets down to the language model in the augmented generation step, along with the original question, and the language model spits out, hopefully, a nice context-specific answer. So yeah, congratulations. You now understand this code, at least at a high level. I will talk a little bit about some optimizations that you can make on this process. And this is a space where there's tons of energy and iteration and research going. It's also a place where I'm still learning a lot and figuring things out. And most of the optimizations, I'll say, come in the sort of like indexing retrieval step. So the first thing is like you can do more complicated embeddings. So in our example, we basically said, okay, take the knowledge snippet, embed it, save it in the vector database. That's what we use for search. But there's no rule that says that that's how that has to work. It's just sort of the simplest way to get started. So one thing we can do is we can add metadata to our knowledge snippets. And so like, let's say we're building a chatbot that helps people navigate visa paperwork. And so we've gone and we've downloaded all the visa requirements documents from like 100 different governments. And then, someone wants to say like, do I need a police clearance to get a critical skills visa in South Africa? In that document, it probably doesn't say South Africa in that section. But we know that the country is really important. And so what we can do is when we're indexing the document, we can take every snippet and we can attach some metadata. So we'll say, okay, for this document, we're going to add country, South Africa, visa type, critical skills. And then when you do the queries, it will then be more likely to find the country or the visa type out. And like, again, this is all text. So metadata isn't like this special concept that you can structure. Like you literally just put this stuff at the top of the text in addition with the document snippet, and the embedding machine will just sort of include that information. Another strategy you can do is you can add other content, and this other content is often sort of also generated by a language model. So in this case, like let's imagine we've built a knowledge base out of like a product documentation or something like that. And instead of embedding the exact documentation, we first ask a language model, okay, summarize this document, or list 10 questions that this document answers. And then we embed those. And that way, when a user asks a question, it's not matching the documentation snippet itself. It's matching like, maybe something that's more likely to match because it's a question that the AI thought that this document was going to answer. So this is another strategy you can use to kind of get better search results. In addition to playing with the embeddings, you can do more complex retrievers. And again, so in our diagram, we took the snippets out of the database and we sent them directly to the language model. But there's no rule that says you can't sort of modify those snippets as they're going in between the database and the language model here on the right. And so like one thing we can do is we could take out the snippets and then add more context. So maybe you do first a search result to get very specific matches, and then you take those specific matches and you expand them to include, the surrounding like 10 other snippets. And this is a way that you can kind of get around that problem of having snippets that are too specific, is if you expand what is being sent to the language model after the search process. And there's tons of other things you can do here in terms of post-processing or trying to make what actually gets sent to the language model more specific. And then lastly, like there's people smarter than me, or at least who know a lot more than me, have like gone really deep in some in many ways to improve things like this. Llama Index is a project that has like all sorts of other sort of structures that it uses for indexing and search. It can do things with sort of trees where you sort of query down a tree and it finds the right nodes and then traverses back up. It also can do things where you first extract keywords and then use those keywords to sort of route searches to specific nodes or specific indexes. I don't know how most of this stuff works. I haven't spent a lot of time doing it, but I know that it exists, and you can go really deep in terms of optimizing stuff like this. Cool. So that was all that I had for today. Thank you for your time, and I will happily take any questions now.
Right. Thank you very much. Okay. I don't see any questions on Discord. Any questions from the room?
Hi, thanks for a very interesting chat. I was wondering, maybe I missed it, but you were talking about private chatbots, so using data that's maybe a bit sensitive. So this approach, I'm taking it, the data that goes in is not being sent off somewhere that it's no longer private.
It depends on the language model. So if you're using OpenAI, then that embedding, the process of getting those embeddings, as well as the chat part, is obviously going to OpenAI. So they claim that they don't train on anything that you do with the APIs. So it's not like that's going to leak into ChatGPT, but you are trusting them to essentially be stewards of your data. And if you have, sensitive data, medical data, or anything like that, then that's not going to work. There are open source equivalents to all of these things. So you can do this like I use OpenAI as an example because it's the most popular and it's the easiest, but you can use, you could run Llama locally on your own infrastructure. And there are open source embedding models that you can use to do the same thing. And then you could really have everything on-prem or in-house, so then you wouldn't be sending your data anywhere.
Hi, thank you very much for the very informative talk. It's very interesting. I would love to hear a little bit more about the knowledge snipping approaches. For instance, I've been dealing with a very long policy documents and trying to build a like a store for these policy documents and helping people search them for specific questions. And of course, they're extremely long and highly structured and referring to other bits and pieces within the same document, and just trying to get my head around that. So I don't know if that sounds. I see you're smiling, so I'm happy to hear what you have to say about that.
Oh well, I mean, mostly it's super hard, and you'll never get as good performance as you would get if you're able to use like Claude, because Claude has a really large context window, so you can upload like 100-page documents to Claude, and then it'll have like the whole thing. No, I was laughing because one of the users of my product is trying to do something very similar with like insurance policies, and we've been just like thrashing a ton for how to make that work. I think metadata at a high level is going to be a really useful strategy there, because you're going to want to associate, like as you're getting these little snippets of text from that policy, you're going to want to add more context that's surrounding that snippet, in terms of just like what section it's referring to or what specific policy it is. And it's that's going to be a hard thing to do sort of without human intervention at this stage, I would think. But that would be my first, that would be the first place I'd look to try and improve things, is like if you have like meaningful section headers or stuff that you can extract to give some of that surrounding context, that's going to be useful, as opposed to just having the tiny snippets of whatever long policy text is in there. That would probably be the first place I'd look. But honestly, I mean, everybody's trying to figure out this problem right now, and it's hard.
We have a question from Discord. Gordon asks, do you mind talking about the merits of LangChain versus doing the plumbing yourself?
No, that's a very interesting question. So what I do and what I would recommend for everybody is to definitely start with LangChain because LangChain it's got so much in it, and you will get up and running. You'll have something you can quickly work on, iterate, and improve. So I'm very much like definitely start on LangChain. LangChain it has a very specific way of doing things, and when you want to break out of the way that LangChain does things, it can be quite hard. And one thing, and there's several things that I've noticed that LangChain is not great at, and one of those things is like having a very customized vector store, which can be which most applications will eventually want, I would say. Like you really want to be able to customize your embeddings and stuff. So that was the piece that I had to break out first and move away from. I have sort of mixed feelings about it in general. Like they are continuing to ship new cool stuff super fast, and they've raised a bunch of money. They've got a bunch of smart people working there now, and so like you do gain a lot of you do get a lot for free if you decide to just kind of stay on the LangChain stack, and you'll be able to sort of use all the tooling and stuff like that. For me, I have found myself mostly using it and then eventually going into the source and either forking it or like rolling my own sort of implementation that's been informed by what they do for like a lot of little pieces of it. But there are trade-offs, I guess. So I guess high level, I would say start with it, try to stay on it as long as possible, but don't be afraid to abandon it. And it's not the type of thing that you have to do one or the other. So like Scriv, my product uses LangChain for a lot of stuff and doesn't use LangChain for a lot of stuff. And you can sort of phase out incrementally, which is pretty flexible.
Last question.
A lot there, yeah.
Thanks again. Can you say something about using knowledge graphs as the knowledge base that you use? So something, maybe some form of RDF that you then split up. I'm imagining that would make the splitting process at least easier.
Yeah, that sounds right. That's not something I have a lot of experience with. That sounds like sort of Llama index territory. So I would take a look at that project. They do a lot with more structured data and graphs and things like that. Llama index is confusing because it's very, very similar to LangChain, but it's also different. So it gets a bit confusing to use because if you're using it with LangChain, they have kind of the same names for a lot of things, and it's kind of hard to tell what you're doing. But my understanding is that Llama index is quite good at that type of operation for that type of data.
Okay, thank you very much. Let's thank the speaker.
Thank you.